All right, good morning, everyone. Uh, we're going to start lesson for 9.1 notes. I probably need to give you a updated calendar later on. The calendar shows a lot of um, problems from the textbook pages, but I did not provide the textbook pages for you. So we're basically just going to be working out of the packet, and the packet will just have classroom problems and AP practice. So I'll give you guys an updated calendar with the associated pages because right now the pages are textbook that we're not going to textbook pages that we're not going to use. Uh, okay, so 9.1. I think this lesson you'll find pretty straightforward. A lot of it you're just using knowledge uh, from first semester AP Calc. So a lot of this I think will come pretty easy to you all. Okay, so I'm going to start. So we've been looking at graphs of one equation with two variables, typically x and y. Now we're looking at three variables that will represent a curve in the plane. In a rectangular equation, that's with two variables, we're able to determine where the object is located at point xy, but with the addition of the third variable, and most often it'll be variable time, or t for time, we're able to determine when the object was at the point xy. Uh, so for instance, if we have a parabola, right, we know where all the points are, but we don't know how the graph is being generated. We don't know which direction it's moving in. So having that third variable t gives us additional information about how the graph is formed, or when the graph, or how the graph is drawn. Okay, so if f and g are continuing functions of t on an interval I, then the equation x equals f of t and y equals g of t are parametric equations, and t is the parameter. We can sketch the curve of a parametric equation by substituting in values for t. So number one, sketch the curve with the following parametric parametricization. X equals 2t and y equals t squared minus 1, with t between -1 and 2. So when t is between -1 and 2, we want to know uh, where these points are, where these x and y values are. So the way we do that is we're just going to plug in, starting at -1, in for x and y, and figure out when time is at -1, where's the ordered pair? Then when time is at -1/2, where's the ordered pair? Then at 0, then 1/2, then 1, 3/2, and 2. And if we were to plug in values that are in between these, if we're able to produce more inputs from t, then we would get an even more detailed picture of the graph. We'll be able to get a graph with more ordered pairs. So let's start. So if I plug -1 in for t, 2 times -1 is -2. If I plug -1 in for y, into the y equation, -1 in for t, I'll get -1 squared, which is 1. 1 minus 1 is 0. So my first order pair when t equals -1 is at -2, 0. So on my graph here, -2, 0. So next up, -1/2. So -1/2 in for t, we'll get -1. -1/2 in for t for the y equation, we get 1/4 minus 1, which is -3/4. So my next order pair, -1, -3/4. I'm just going to estimate to the best of my ability where that -3/4 is. All right, 0 in for t. Right, 0 in for t for the y equation. Okay, just going to fill in the rest of my order pairs here. Plug 1 in, plug 3 halves in, plug 2 in, so we see the graph being formed, and we see how it's being formed. It starts here and it kind of moves this way. So this ends up being a equation for a parabola, but we have more detail in terms of not only where the graph is, but how the graph is getting formed. So the arrows indicates the direction that the graph is moving in, or the graph is being formed. We can also ask the calculator to graph something in parametric form. So in your graphing calculator, you can go to mode, and then you can choose parametric. You're going to see that PAR. So in your graphing calculator, if you have it on you, go to mode, and then scroll down. Right now, you're probably in function mode. So you can scroll over to PAR for parametric, highlight that, hit enter, and then now go to y equals. Now, once you're in parametric form, all your variable is going to be turned in terms of t. So we're going to plug in this parametric equation here. So x equals 2t. So whenever you press on this x, now it's going to select the variable t for you. So go ahead and type that in. So 2t in for x, t squared minus 1 for y. So that this is the window is, we can set these window settings to allow for the graph to show up to look like this. So if you can go to Windows and then type in these settings here. So tmin at -1, tmax at 2, tstep at 0.2. So this just indicates the increments of t values that we're plugging in. The smaller your steps are, the more the graph is going to gather more order pairs along the way. Xmin, -3.5, Xmax is 5. X scale, Y scale, we leave both at 1. Ymin is -2. Okay. -2, and Ymax is at 4.5. It doesn't have to be exactly this. It's just easier to see the graph that way. So then once you enter them in, hit graph, and you can see the parabola showing up, and also the movement of the graph in terms of how it's being formed. Okay. Now, what we can also do is we can take something in parametric equation and turn it into what we are more familiar with, a rectangular equation, in terms of just x and y, a normal quadratic function. So let's see if we can try that as well. So number 2, to find the rectangular equation, when you are given the parametric equation, we can eliminate the parameter t through substitution. So we just want to get our equation in terms of just x and y and remove the t variable. So we want to solve for t first. Choose the equation that is easier to solve for t. I'm going to choose this x equals 2t here. We don't have to worry about dealing with square roots if I choose this one. Um, so we always prefer to choose the easier one to solve. So this is x equals 2t. I'm going to solve for t. So divide both sides by 2. So now that I have x over 2, I'm going to take that and put it into my y equation. So I know t is x equals x over 2. So I'm going to take this x over 2 and put it into the t of my y equation. Okay, so y is equal to x over 2 quantity squared minus 1. Let's do some cleanup here. This is x squared over 4 minus 1, which is, this is fine, but we can pull that 1/4 out. So this is basically a wider version of our parent graph, y equals x squared minus 1. It has a y-intercept at -1. So this is a function that we're more familiar with, but by eliminating the parameter, we get into an equation that we recognize, but also we remove the additional information in terms of how the graph is formed. Okay, let's try another one where we are starting with parametric equation form and trying to get it down to just x and y. So this one, we're going to eliminate the parameter, recalling a Pythagorean identity. So we know of an equation that can allow us to link x and y together, and that's Pythagorean theorem. We know that x squared plus y squared is equal to, oh, sorry, we know that, let me first start off. We know Pythagorean identity, sine squared plus cosine squared equals 1. So if I know that this is an identity I can work with, I can replace 2 cosine of t in for that sine squared, or we're going to try to get it into um, this form here. So I can isolate cosine and sine. We know that x is equal to 2 cosine of t. So therefore, x over 2 is equal to cosine of t. Likewise, y over 2 is equal to sine of t. So if I make that substitution, we can replace sine of t with y over 2. We can replace cosine of t with x over 2. Make that substitution. So I get y squared over 4 plus x squared over 4 is equal to 1. We've eliminated the parameter. We've got rid of um, uh, the t's by replacing sine and cosine in terms of x. So now if I multiply everything through by 4, we should be able to recognize this equation here. So this should be more familiar to us. This is a circle equation with the center at 0, 0, and a radius of 2. So a graph that looks something like this. Okay, next page. Here is the derivative of a parametric equation. So derivative we know is dy dx, which we can rewrite this in different form, y prime. We can do a derivative with respect to time. So we can do y prime of t divided by x prime of t. And then y prime is basically dy dt. So it kind of has that related rates feel to it. So if I want to find the derivative of an equation that is in parametric form, I just need to find the derivative of the y component and the derivative of the x component, and then divide them over each other. So given our parametric equation, x equals t to the 1/2 and y equals 1/4 t squared minus 4, find the derivative of y with respect to x. So really, we can just find the derivative of y prime with respect to time, find the derivative of x with respect to time, and then just divide the results. Let me just clean up y a little bit here. Y of t, I'm just going to distribute that 1/4 through. So 1/4 t squared minus, distribute the 1/4 times -4, I get -1. So I'm just going to follow this formula here. So dy over dx is just y prime divided by x prime. This is already in terms of time here. So when we find the derivative, we don't attach a d over dt. I mean, technically it's dt over dt, but we can leave that out since we know t is already the independent variable. So y prime is power rule. So bring down the 2, so 1/2 t. The 1 goes away because that's a constant. And then t to the 1/2 is derivative. We can just go through power rule. Now we can clean this up. Whatever the cleaned up version of this is basically our derivative. The 1/2 can cancel out. I can merge the variables together by bringing this t up to the top. T to the negative 1/2 in the denominator, same thing as t to the 1/2 in the numerator. Add the exponents. 1 plus 1/2 is 3/2. Right, number 5, given x equals e to the 2t and y equals cosine of t, where t is greater than or equal to -1, find the equation of tangent line when t equals pi over 2. So we're going to find slope the same way as we did for number 4, but we can also find order pair by plugging in the t equals pi over 2 and for x and y, get the x and y values. Once we get our x and y and our derivative and our slope, we can do point slope form. Okay, let's find the order pair first. We're just plugging t in for the x and y into the t of the x and y. So e to the 2 times pi over 2 becomes just e to the pi. Okay. Plug pi over 2 in for t, cosine of pi over 2. Using your unit circle knowledge, you know that cosine of pi over 2 is just going to be 0. Okay, so there's my order pair. I'll come back to that later. Okay, derivative dy over dx is just y prime over x prime. So the derivative of cosine is negative sine. Derivative of e to the 2t. E to the u's derivative is e to the u times u prime. Take our derivative, plug in pi over 2 to get our slope. So negative sine of pi over 2 over e to the 2 times pi over 2. That's just going to be 2e to the pi. So that ends up giving me negative 1 over 2e to the pi. All right, we have everything that we need to build our tangent line equation. We have our order pair. We have our slope. And then point slope form. Uh, so our eventual homework, it's just going to be these pages here. So pages 2 through 7. I probably won't make this homework due until after we have our quiz, but just kind of give you an idea of what we're working towards. And so for the rest of class, we'll just work through as many as we can, um, and then whatever we don't finish will be our homework. But I'm not going to set a homework date when this is due until after we get back into school. So probably be um, Friday or Monday. Right. So number one, for the given parametric equations, eliminate the parameter and write the corresponding rectangular equation. So I'm going to try to solve for t. I think it's easier to solve for this one. This is less going on than this. So if I want to solve for t, I have to find a way to bring that t down. And anytime I want to bring a exponent down, I can involve natural log to help me get that to happen. So I'll take the natural log of both sides. Natural log of e is just 1. So negative t equals natural log of x. So t is equal to negative natural log of x. So we're trying to eliminate the parameter, so we always are going to try to solve for t of the easier equation, plug it into the other variable equation, and try to get our equation purely in terms of x. So I'm going to plug this in for the t. I'm going to try to find a way to clean this up here um, using log properties. Also have e and natural log here, so I should be able to get these to work together to clean this up, cancel out. So let's see if we can do this. We know this is within a log expression. I'm going to push that -2 up as an exponent just to kind of rearrange and help me see some properties here. If I write it this way, I can now see a little bit more clearly what I can do here. E and natural log of x. These are inverse functions. They can cancel each other out. So if they cancel out, then I'm just left with x to the -2, right? E and natural log goes away. The only thing left is that x to the -2. So y is equal to x to the -2 minus 1, which is the same thing as 1 over x squared minus 1. Number 2, let C be a curve described by the parametricization of x equals 5t and y equals t to the 4th plus 3. Find an expression for the slope of the tangent at C at any point, x, y. So we're just trying to find dy over dx. So just y prime over x prime. So y prime is just 4t cubed. X prime is just 5. That's it. The position is given by x of t and y of t. Find dy dx as a function of x. Basically, we'll get our equation down in terms of x and y, and then we can find the derivative once our t variables are gone. Or we can do this. We'll just find dy over d. We'll just find y prime over x prime. And then once we find the derivative, maybe this is easier here. We'll just find the derivative like how we did for number 2. And then we can make our substitution at the end. Just make sure that our t's are replaced in terms of x. So let's just do y prime over x prime. Y prime, power rule. 2t squared. And then x prime is just 6t. So t over 3, I need to find a way to get the t in terms of x. So I'm going to rearrange this equation to help me do that. So to the side here, I know that x is equal to 3t squared plus 1. Let me see if I can isolate the t so I can get my derivative and just in terms of x instead of t. Divide both sides by 3. Take the square root. Now I'm going to make a substitution here. This can go in for that. So it says t is greater than or equal to 0, so I know I'm going to take that plus, there's a plus or minus from the square root, but I'll take the positive square root version of it since t is greater than or equal to 0. So it's this divided by 3, or it's 1/3 times t. So let's just pull that 1/3 coefficient out. Okay, so there we have it. We have our derivative in terms of x instead of t. Number 4, a particle moves along the curve xy plus y equals 9. If x equals 2, dy dt equals 3. What is the value of dx over dt? So we want to find the derivative, but now there's a little bit of related rates here, right? We can find the derivative with respect to time and get all these variables to show up, dy dt, dx dt. So we'll do related rates. And also x times y, we got to go through product rule as well. Okay, f prime g plus fg prime for that xy portion here. So f prime, x becomes dx dt. G is the y. Back to f. G prime, dy dt. Y's derivative is 1 dy dt. And then the 9 goes to 0. So dx dt is what we're looking for. That's the unknown. Dy dt I can replace with 3. X I can replace with 2. Dy dt I can replace with 3. The only thing missing is I don't have a y here. So how can we get that y value if they don't give it to us? Well, they gave us x equals 2, and they gave us the equation, so we may have to plug into the original equation and solve for y on our own separately to use in our derivative equations. So off to the side here. I'm going to plug 2 in for x, see if I can solve for y. So 2 in for x. So I get 2y plus y equals 9. 3y equals 9. So therefore y equals 3. So now I have everything for me to find my dx over dt. The only variable left over is dx dt, so just going to combine terms and try to solve for dx dt. So I get 6 plus 3 is 9. Subtract 9 from both sides, divide by 3. All right, let's try a few more. Next page. A curve is described by the parametric equation x equals t cosine of t and y equals t sine of t. Find the equation of the tangent line to the curve at the point determined by t equals pi. So this is a little similar to what we did with number 5, right? Finding the derivative, taking that t variable, plugging in, finding our ordered pair, finding our slope, then point slope form. But maybe this is a little bit more complex because the derivative process may require more than just cosine becomes sine and sine becomes, or cosine becomes negative sine and sine becomes cosine. That t cosine t, that t sine of t, these are two variables being multiplied together within each equation. So within each, we have to go through product rule. So be careful of product rule here. Let me start off with order pair though. So plug pi in for t. You get the x and y at those points. Okay, derivative. We know derivative uh, in parametric form is just y prime over x prime. Product rule, f prime g plus f g prime. F prime g plus f g prime. And then once you have the derivative, we can plug in pi in for all the t's to get our slope. Sine of pi, 0, pi, cosine of pi. It's going to be pi times -1 or negative pi. Pi in for cosine in the denominator, so cosine of pi, which is -1. And then pi sine of pi, we know sine of pi is 0. So I'm just left with negative pi over -1, which is pi. That's our slope. Now point slope form. All right, let's do one more here. Coordinates x and y of position of a drone changes at rates given by x prime and y prime, where x and t are measured in meters. At what time does the slope of the line tangent to the path have a slope of 1.5? Well, we're basically given what derivative our slope is, right? They already gave us y prime and x prime, so we just divide them over each other. There's no need to find a further derivative. We just have to get it into this y prime over x prime here. So t to the 1/2 over 2t cubed. I'm going to just clean up with positive exponents. So I'm going to move this down here. So 3 minus 1/2, the same thing as 6 over 2 minus 1 over 2, which is 5 over 2. I'm trying to figure out what is the slope of the line tangent. So the slope of 1.5 means that my dy dx equals 1.5. So at what time t, we're trying to solve for t when the slope is 1.5. So I have enough information to plug in. So 1.5 can replace dy dx, and I can just algebraically solve for t here. I'm going to just cross multiply and get rid of the denominator and then solve for t. So if we use our calculator here, um, we can undo that 5/2 by raising both sides to the 2/5. We use our calculator, 1/3 raised to the 2/5 is around 0.644. So if you want to get ahead with the homework, you can, page 2 through 7, um, but I'm not going to make it due until later this week or early next week. Uh, I will record this lesson and put it up on my website and also send you guys a link to the page where you can find the full key for these worksheets as well as key for your AP practice. Okay. All right. Have a great day, guys.